Now that we've derived the lower and upper bound on the error term in the integral test, let's see some applications of this. So I want to look at one particular series and then consider several different things we could do with this based off of what we know about error. So the series we will look at is this one that is the sum from k equals 1 to infinity of 1 over k cubed. So first question here is, let's suppose we want to find bounds on the error incurred by approximating this series by its 10th partial sum. Okay, so a question like this is pretty much directly asking us to take advantage of the lower and upper bound on the error that we saw in a previous video. So we're looking at what we've kind of used notation-wise as e sub 10. I'm taking the error that I get if I simply add up the first 10 terms of the series and use that as an approximation of the infinite sum. What we saw before is that the error can be bounded by integrals of the associated function. So the terms are 1 over k cubed. The associated function then is 1 over x cubed. In order to get a lower bound, if we're using the 10th partial sum, we saw that we put 10 plus 1, or 11, as the lower limit of integration. And on the upper bound on the error, we use 10, which is the end value. And both of these we integrate up to positive infinity. So what I need to do here is evaluate these integrals. So the integral from 11 to infinity of 1 over x cubed, or x to the minus 3, this is improper, so I express it as a limit. The antiderivative of x to the minus 3 is negative 1 over 2x squared. We're evaluating that from 11 to b. And this leaves us with 1 over 242. Plugging in b, we get 0. We're subtracting a negative, so we add it. 2 times 11 squared. Now, to find the upper bound on the error, we can kind of take advantage of the work where we already found our antiderivative. The only difference is now we're evaluating this from 10 to b. So this is going to give us 1 over 200. Putting this together, then we know that our final answer to this question is that we can say that the error would be bounded above by 1 over 200 and below by 1 over 242. Notice that if I simply add up the first 10 terms of the series and say I want to use this to approximate the infinite sum, what we have here is an idea of how good of an approximation that is. We can see that, and often we're more concerned with, say, that upper bound on the error. We would like to ensure that that is relatively small, so that would tell us that we have a good approximation. Okay, so that's the first question with this series. Same series, but now we want to answer something else. Given that this 10th partial sum, in fact, is equal to 1.1975, let's use your answer to A, or to 1, I will say, the question we just looked at. Use our answer to 1 to find bounds on the sum of the series. And when I talk about the sum, I mean the infinite sum. So we know the sum from 1 to 10 is given in this question. And so given the knowledge of the sum from 1 to 10, and also our error bounds in that case, we want to produce bounds on the whole sum of the series. So that comes down to remembering how we defined the error. So remember here that e sub 10 is the true value of the sum, which is of course unknown, minus the 10th partial sum. So that means that if I want to now focus on not e sub 10, but simply the entire sum, let's add S10 to both sides of the expression I have there and observe that we have that's equal to the E10 plus S10. So knowing that E10 has bounds that we found above, what I want to point out here is that if I want to translate that into bounds on the infinite sum, I can simply add the 10th partial sum to everything. So this says that E10 plus S10 would be bounded below by 1 over 242 plus S10 and above by 1 over 200 plus S10. So that means, so this part that I have in the middle, that is equivalent to the entire sum of the series. We're saying that that's bounded below by 1 over 242 plus 1.1975 and above by 1 over 200 plus 1.1975. So that would, again, give us an interval of values where we would know that the true sum of the series would fall somewhere within that interval. Again, the goal is hopefully that interval is pretty narrow, telling us that we have a pretty good idea about what the sum of the series is. Another question, same series, is we could kind of shift the focus to what the unknown is. So far, we've been given a value of n, 10, and asked to kind of gauge the error that results in using the nth partial sum. So alternatively, here we're asked how large must n be so that we can ensure that the e sub n is bounded above by 1 over 200. Now, keep in mind that I've chosen this n value. We've already been working with 1 over 200 above, so we have an advantage here that we have a little bit of insight into where that 1 over 200 would come from. But imagine that this was a question asked without the prior work in parts 1 and 2 of this. The way that we would tackle a question like this is, again, to go back to what we know. Remember, e sub n here is referring to the error and using the nth partial sum to approximate the infinite sum. So we know that e sub n is bounded above by the integral from n to infinity of 1 over x cubed. That's what we know. We also know that that integral evaluates to 1 over 2n squared. So I know that an upper bound on e sub n is 1 over 2n squared. In order to ensure that e sub n is in fact bounded above by 1 over 200, note that it suffices to have the situation in which 1 over 2n squared is bounded above by 1 over 200. So just to make sure that's clear, that's because I know that this inequality holds. What I'm stipulating here is, let's ensure that, in fact, 1 over 2n squared is bounded above by 1 over 200. Automatically, that means that e sub n is likewise bounded above by 1 over 200. So I'm not saying that this is necessary in order to ensure that e sub n is bounded above by 1 over 200, but it certainly is sufficient. So that would be one way to make sure this would happen. And it's kind of all we have to work with. And so in this case, the inequality here gives us something to work with. So I want 1 over 2n squared to be less than or equal to 1 over 200. That's equivalent to needing 200 to be less than or equal to 2n squared, or 100 being less than or equal to n squared. And taking the square root of both sides, we get that we need n to be greater than or equal to 10. So this tells us how many terms we should expect to add together so that our resulting finite sum, so the sum of those n terms, is what we might think of as close enough to the true value of the sum. So if I have some kind of information going into this question about when I know that my approximation will be good enough in terms of bounding my error, this approach would allow us to figure out how many of those terms we would need to add together until we reach that level of confidence.